I'll skim over the first historical aspect of it. Like, we'll just see, you guys know what all happened before the periodic table, right? Pehle, very few elements were discovered, so people didn't really have a need to, classify them or know. Like, if they knew what individual element did, it was sufficient. But slowly, like as the elements started getting discovered, Dobriner noticed something strange about all these elements. What did he notice? Do you remember?
The triads.
Triads, yes. The people started noticing that some elements were very similar to each other and very different from others. Like they started looking at families of elements, alkali metals and halogens and all that. Uske baad, what was the next development? Do you guys remember?
They discovered that like after every octet, like the first element was similar.
Absolutely. Newton's law of octaves. So if you arranged all these elements in the increasing order of their atomic mass, now all of this was in 1800s. So if you remember structure of atom, people didn't know properly about how electrons are there, like how it affects the valency, atomic number. All of that happened in early 1900s. So whatever classification was happening, it was 1800s. Okay. So if you arrange them in the increasing order of atomic mass, every eighth element repeated. So wahan pe periodicity ka idea aa gaya. But because there were a lot of missing elements in between, it was still, like, okay, it was okay for the first 20 elements. Uske baad it just got mixed up. Then, landmark moment, Mendeleev created his periodic table. And he is considered father of the periodic table. Like he could have come up with the modern periodic table that we used if only the whole concept of atomic number was discovered during his time. So he was limited by the fact that people worked only with atomic mass. So he worked the best he could with available information, and he created his own periodic table. So that had its own merits, demerits. Do you guys remember some of the advantages of Mendeleev's table? No? Would it help if I just show you guys Mendeleev's table screen pe? Okay. Oh yeah, there's a like really big hint right here in this thing. Yeah, now do you remember like what was like the one big advantage with this table?
It left places for like undiscovered elements.
Yes. So his table, the whole purpose of creating like a periodic table sort of a thing was to make the study of elements easier. So if we know that lithium, sodium, potassium all behave in the same way, once you know that properties of sodium, you don't have to study potassium separately. There'll be only minor differences, but 90% they're the same. Like both have the same valency, the kind of physical properties, chemical properties they show. Like it's gonna be very, very similar. Like 90% of your work is done. So Mendeleev's table is so accurate. He went by grouping similar elements together, which was the whole purpose of creating the table, and he could predict undiscovered elements. So these are the pink things that in this particular image, that Mendeleev knew there was some element there. He didn't know what it was, but because of the placement, he could predict their properties also to a very good degree of accuracy. Properties in the sense, what its mass could be, what its boiling point, melting point could be, what kind of compounds it would form, like stuff like that, valency, all of that. Okay, and so yeah, like discovering new elements did not disturb Mendeleev's table. But again, Mendeleev had his own problems. Some of the problems, like just so he could group elements together, he went against his own rule of, arranging them in increasing order of atomic mass. Like there were some cases where something of a lower mass was placed after something of a higher mass, like cases like those. Okay, and position of hydrogen, like hydrogen is outright non-metal, it's a gas, and it is capable of forming covalent compounds and all that, yet he grouped it with this thing, so that was an anomaly, things like that. Okay, so Mendeleev's table happened in 1800s, like 1869 or something like that. Okay, and after that, in the 1900s, oh, Kaveri came and went. Okay, so in the 1900s, the atomic number was discovered. Okay, so once the atomic number was discovered, it was this guy called Henry Moseley. So Henry Moseley, yeah. So Henry Moseley was the one who first put thought into it. Like once the proton neutron was discovered, once people started using something called the atomic number, he found that atomic number is pretty significant, and through experimental data, he could show that the atomic number directly affected the physical and chemical properties. Like he had this formula also, which you guys don't need to remember like this. It's just mentioned for your information type. So if you want, I can give it to you. Otherwise, like you won't have numericals and all based on that. Yeah. So the atomic number is the more fundamental property, and that he said that the square root of the frequency, so this is the square root of the frequency of the X-rays emitted by the element, is directly proportional to its atomic number. So thus you don't need to worry. Basically, he's done some spectroscopic studies and figured out that, just a moment. So he did some spectroscopic studies and figured out that the atomic number is the more fundamental property, like it relates with everything else. And so Moseley just modified Mendeleev's table. So Mendeleev went by atomic mass, right? So Moseley took the same principle and created the modern version of the periodic table using atomic numbers. So he did the same thing Mendeleev did. He arranged all the elements as per the increasing order of atomic number, and also took care that the similar elements were placed together. It was not like a random table that he created. Okay. And the result of that is your modern version of the periodic table, the one that you guys are all familiar with. And that's the periodic table. Okay. So this is like the brief history of periodic table. This is how it had come to be. Yeah. So now this whole chapter is we're going to talk about why the periodic table is pretty important, like things fit like jigsaw puzzle. And the rest of it is like, how do you make use of this periodic table? So using the periodic table, you'll be able to figure out the electronic configuration of an element, and the other way around. Like if you know the electronic configuration, you can figure out which block it will sit in, which group, which period, and all of that. And once you know the position of the element, you can easily figure out if it's a metal, if it's a non-metal. You'll get an idea of, is it going to have a relatively high ionization enthalpy? Is it going to be reactive, less reactive? What its valency is going to be? All of that stuff. So the rest of the chapter is just learning how to get all of these details. Okay. So if you look at the periodic table, what are the main features that you guys would observe in this?
Metals, metalloids, and non-metals.
Like the metals are starting from the left and the non-metals are from the right, and the metalloids are in between.
Somewhere
And
in the
then
middle. Yeah, absolutely. So for that, you need to like go through each element and all that. But what's the first thing that you guys observe? So this is in tabular format, right? Table ka matlab it's gonna have rows and columns. So how many rows are there? What are they called? How many columns are there? What are they called?
the rows are called groups, which are like 1 to 18. And
Rows,
then there are,
wait, rows are horizontal.
yeah,
So are they called groups or periods?
groups. And then the
Is he correct?
column, yeah,
18 groups
No,
and 7
18
periods.
groups and 7 periods.
yeah, I was saying that only. Rows are groups only.
Horizontal rows. Matlab, if I isolate, let's say this row, lithium se leke neon tak, is that a group or a period?
Group.
No. So horizontal rows are called periods, and the vertical columns are called groups. Okay. So you can, like, you got the numbers right. So you said 18 groups, right? Like 18, what are there 18 of? So vertical column number 1, vertical column number 2, 3, 4, 5, 6. So there's 18 groups. So 18 of the vertical columns and 6 or 7 of the horizontal groups. Okay. So all of you know of Harry Potter, right? Yeah, so there's a mnemonic to not get confused. Harry Potter, very good. So horizontal periods, vertical groups. Yeah, that's it. If there's anything else that you guys would want to prefer, like for HPVG, you can make one on your own. But yeah. Yeah. So the horizontal rows are called periods and the vertical columns are called groups. The 17 of the periods. So if you count how many horizontal rows are there, 1, 2, 3, 4, 5, 6, 7 periods are there. And if you count the number of vertical columns, there's 18 of them. So 18 groups. Okay. So this is like the most basic thing. The periodic table is divided into blocks. So we'll take up each block one by one. So there's total of 4 blocks in the periodic table. So you've got the S block, you've got the P block, you've got the D block, and you've got the F block. Yeah. And okay. Now let's dig a little deeper into it. So there's 7 periods and 18 groups, right? The groups represent a family of elements. Okay, so all the similar elements you will find in a single group, or elements with similar physical and chemical properties. So all elements in a group will have similar properties. So you can think of it being like a family of elements. So just like how families have like a first name, like first name is an individual one, and then you have a family name, right? Like a surname, a last name. So similarly, each of these family of elements also, we give name to some of them for easy identification. So that way, group 1, these elements are called alkali metals. Do you know why they are called alkali metals?
Because they're bases that dissolve in water.
Correct. So all of these elements will form bases, and all the bases are able to dissolve in water. And usually these soluble bases are called alkali. Like before we call them like acid bases, the ancient Greeks, Romans, whoever dealt with these, they call them alkalis. So that is the reason they're called alkali metals. And on a similar vein, group 2 elements, where do I write it? So these elements are called alkaline earth metals. Okay, so the logic is same. So these metals also form bases. They're basic in nature. They're like alkali. That is why alkaline. Earth metals, because you will find a lot of these metal salts in the earth. Like you have Epsom salt, magnesium sulfate, calcium salts. You have gypsum in the earth. You have marble, limestone in the earth. So strontium, barium also, like barytes and all. So you find a lot of these salts in the earth's crust. That is why they're called alkaline earth metals. And another thing, the reason we don't have a name for every single group is that these names, like people identified that some metal, like some elements were similar to each other. So they called them, like they grouped them and then gave them a specific name. So all the, like, and all of this was done before the periodic table was formed. So whatever names you find, you will find them for like elements that have been known for a long, long time. So wherever there's newer elements, that's why the D block elements, a lot of them, these groups don't have a specific name as such. Then coming to this corner, group 18, well, this you just know it as noble gases because you just have noble gases in them, all the inert gases. Group 17, oh, name is given here. I don't know if it's visible. So this is a popular group, popular family. Now, do you know what is the name given to this group of elements?
Halogens.
Halogen. Yes. Group 16 also has a name: oxygen, sulfur, selenium, tellurium, polonium. Do you know any, does anyone know the name for this?
Chalcogens.
Chalcogens is correct. And group 15, you can see here, they're called mycogens. So P is silent, P-N-I-C-O, mycogens. Uh, 13, 14, 13 doesn't have a name as such. 14, I don't, like there might be, but it's like not very well known. It's not like one of the popular ones. So mostly in your study, you will come across alkali metal, alkaline earth metal, and halogens. Chalcogens also is relatively less, and group 15 ke liye, like barely anyone calls it by the name. But halogens is pretty popular. Like every time you study any physical chemical property, it'll be called like reaction with halogens or halides and things like that. So if we come across the word halogen or halide, halogen matlab it couldn't stand for any fluorine, fluorine, bromine, iodine. Halide matlab it's the ion of it, the chloride ion, bromide ion, fluoride ion, that way. Okay. There's two more families, I forgot. So at the bottom, F block may, you've got this horizontal row, all this particular group of elements. They are called lanthanides. And this group is called actinides. So it's not like the vertical group, it's just this whole bunch of elements together. They're called lanthanides, and this bunch is called actinides. So they're all completely F block elements only. So the F block elements following the element lanthanum are called lanthanides, and the F block elements following actinium are called actinides. And you can see the relation, right? So they are following lanthanum, and all of these elements are similar to lanthanum. इसलिए lanthanides. And all of these elements are similar to actinium. That's why it's actinides. So EM ko nikal ke just put IDES, lanthanides and actinides. Like lanthanum, like actinium. Okay, what else can we talk about this? So sometimes in your textbook, like lanthanum, lanthanides, instead of that, you may also come across the word lanthanoids. Both are right, come across both. Lanthanide, it's OIDS instead of IDS. Lanthanoids and actinoids, either or. Yeah, that's one thing. What else do we have? Lanthanoids, actinoids. Yeah.
Why are all like inert atoms gases?
Oh, that's easy. You can figure it out yourself. Okay. What is the difference between solids, liquids, and gases?
Intermolecular space.
Yes. And also another property?
Molecular forces,
Intermolecular forces, correct. Right? So abhi agar do atom ke beech mein agar kuch, like if you want them to force together, there needs to be a reason for them to stick together. So for example, metals are all solids because the way they are arranged, like metals are electropositive, right? So they can give away their electrons easily. So what happens is when you, like in a block of metal, the atoms are arranged side by side, and the valence electrons are not bound to the atoms. So they're all roaming around in between the metal atoms freely. It's called sea of electrons. You can think of it as, there's a sea of electrons, it's a blob, and then the metal atoms are all arranged in between them. And that gives rise to the malleability, ductility also, because they're all held together by the electrons constantly flowing. You can't break them easily, like the electrons are holding them together. Now, in the case of noble gases, because they are inert, like because their valency is zero, like they have octet configuration all filled up, are they capable of bonding with other atoms? No. So that is the reason each atom is independent. There's nothing holding them together. So the intermolecular forces are like really, really low, and they're all, just roaming around their gases. Okay. So you'll learn all about this in detail in the chapter states of matter. Like you have properties about gases, about intermolecular forces. So there's something called van der Waals forces, London dispersion forces, dipole forces, all of that stuff. We'll get into that. Okay, now significance of the groups and periods. Okay. So can I like erase all the things that are written? Okay. Now, significance of groups and periods. Like group, I already mentioned that they all contain, they are a group of elements, it's a family. So they all have, like you have similar elements with similar properties in any single group. Now, what is the significance of periods? Why are the horizontal rows called periods? Can you think of reason why? Like, observe what is happening after every period. Any idea? So if you look at the second period, lithium का पूरा रो होने के बाद नियॉन तक जाके when is the next row starting again?
When like the principal number is 3.
Let's not go there. Like we haven't talked, like this is again like extremely basic. What's the first thing that you see? Like second period hai, you have lithium, beryllium, boron, carbon, all of these are in a single row. Uske baad, neon ke baad, the next element you started in a new row, like you didn't put it over here. So like, why is that the case? Like what's happening after at every single row?
They're filling like an octet.
If octet is filled only in inert gases, like what's happening when you go from neon to sodium? Like why is sodium in a new row and not continued in the second row like this?
After every noble gas, it goes down
Yeah,
in
why?
the next period.
Why?
Because it's similar to the first element.
Similar properties.
Correct. Ritu Smera got it. So every row begins when the properties are repeating again. Okay, so naya row, sodium takes after lithium, magnesium takes after beryllium. Similarly, फिर potassium takes after sodium, calcium takes after magnesium, and gallium takes after aluminium. So like the rows signify the repetition of properties. So you can observe the periodicity in properties at every row. That is the reason your horizontal rows are called periods. Okay, so that's like the significance of the name period. Group, because you have a group of elements. Like if you were to group elements based on similarity of properties, you'd group those particular elements together. That's why the vertical columns are groups. Horizontal rows are periods because they signify the periodicity of the properties. Every time you begin a new row, the same properties are repeating again. फिर नया row में same properties are repeating again. That way. Okay. So these are like your major features of the modern periodic table. We saw that there were horizontal rows, vertical groups. Why are they called rows and groups? We saw that there are 4 blocks, and then we went over some important like families of compounds, and we saw like how the elements are arranged, atomic number के हिसाब से, increasing order. Okay. So before we get into like the in-depth properties of individual blocks and the trend of properties in a row and period, there's a little bit about nomenclature of elements. Okay. So like pehle, like all the old elements, like people have been calling them that ever since they were discovered. So their names are set. But what about the new elements that have not yet been discovered? Like, what if somebody discovered an element like tomorrow? Who decides the name? Like, how do you name it? Right? So do you guys remember, like, you had heard of this, we have studied this earlier. Do you remember this acronym? Yeah. What is the context? Like, how do you remember it?
No, I remember you said
Decided the name.
Yeah, like the methane ka formaldehyde, the thing you told us.
Ah, correct. Organic compounds ka name, right? Yeah. So IUPAC, this stands for International Union. This is again just for your information, huh? You won't be asked. So this stands for International Union of Pure and Applied Chemistry. Okay, so if at all there is like chemistry overlords, these are the people. So these are the people who decide everything, who give approval of, you know, what Avogadro's number should be, what the element name should be, what compound name should be, what standard method you have to follow, what is the pattern you have to follow, like all of that stuff. Because the world is a really large place, like different countries have different languages, different countries have different metric systems, like measurement systems. So there needs to be one standard, like how the units ka decider, you have like SI system of units, who decides like what is length, what is mass, what is time, all of that. Similarly, for all things chemistry, you have IUPAC. Okay. So when a new element is discovered, nobody can just, like, anybody can claim that, look, this is something new, it's a new element, its atomic number hai 120, and this is what I've found out, right? IUPAC is going to first verify if those claims are true. Until then, it's not going to be like, you know, publicized, or, you know, textbooks are not going to be changed, like all of that's going to happen. And IUPAC is the one, like, during this process of verification, to ensure that it's not a mistake, like mistakes can happen. It is definitely a new element, and it's not just, you know, a case of two independent research organizations finding the same thing. Like, they verify all of these claims. So during that process, they have a temporary system for naming new compounds. Okay. So this, until people can decide on a name that everybody is happy with, IUPAC decides that, okay, like, iska temporary name will follow this particular format. Okay. So after that, again, the permanent name is usually in the honor of either the country where it is discovered, or the person who discovered it, or a related, you know, like some scientist who has won a Nobel Prize. Like, that's why you have Rontgen, which is in honor of, you know, Rontgen who discovered X-rays. That's why you have Curium, you have Mendelevium, you know, names in honor of people. You also have stuff like Germanium, which is in honor of a country, Germany. You have Francium. What else? Thorium is in honor of the Norse god Thor. Neptunium, uranium is again
There's
platinum.
also Californium, right?
There's Californium, yes. There's Americium or Americium, yeah. Okay, so all of these names are decided by IUPAC. If IUPAC wasn't there, there is definitely going to be chaos. In fact, if you're interested, there's a whole wiki page on controversies behind naming. Because maybe two independent scientists, or maybe it's a team of scientists who have worked on discovering this thing. And then, you know, the Russians want to name it after a Russian scientist or someone on their side. The Americans want to name it on something on their side. And there's going to be whole disputes, like, do we call it this or that? Yeah, to avoid all of that, IUPAC is going to step in and then say that, oh, no, this is going to be the name. So until it can, like decide on a name that everybody is happy with, there is a completely neutral system of naming. So a neutral system of naming depends on the atomic number. And the name itself is basically just the atomic number changed into words. Okay. So every number has a, like, you have Latin equivalent of the numbers, right? Like, for example, 1, you use un. That's where your unicycle comes from, because it has one wheel that way. 2 is bi. 3, can you guess what is for 3?
Try.
Try.
That's it. 4,
What?
Quad.
5,
Is it that?
And
pen.
Pen.
That's it. 6,
6.
hex.
hexagon. Yeah. 7,
Have?
Step.
it could be hept or sept. In this context,
H.
the sept, I think. Yeah. 8,
Oct.
yes. 9 is again different. So it's not non, it is N, EN. Okay. And 0. And 0 ke liye it's nil. Shunya. Nil. Okay. Now, the naming system, suppose you have, so it's basically the atomic number. Name will be the atomic number plus IUM. So for example, you have an element newly discovered which has atomic number, say 112. So 112, 112 in name, like what is 1 in words? Un or UN, right? Uske baad second digit is also 1. Again, it's UN. And then what is the word for 2?
Bi.
Bi. End it with IUM, because that's how elements are, like sodium, potassium, IUM. Okay. That's it. So this is like the temporary name. And symbol is you just take the first letter of each of these numbers. So an ka first letter is U. Dusra bhi an hai, so that's U. And bi ka first letter is B. That's it. Okay. So the format remains the same. Like hamesha, when there's multiple letters in your names, only the first letter is capitalized. Baki sare should be small letters. So you follow the same thing here also. Like we have chlorine, C is capital, L is small. So that's what you follow here also. The first letter is capitalized. Baki sare will be small. Okay. So you guys figure out the names. Let's say you have 109. इसका नाम क्या होगा? Chat पे भेज सकते हो if you want. You can type out the spelling. Oh, one tiny little correction, you guys. 9 ke liye ENN, you have double N here, not single N. Okay, it's my bad. But yes, Ritu sent correct. Yes, Smera sent correct. Arnav, yes. Adat, yes, absolutely. You guys got it. That's un, nil, n, nium. And the symbol is UNE. That's it. That's all there is to it. Nomenclature ke liye, UPSC
I
nomenclature.
have a question.
Yeah.
I'm just wondering. You said that like the last few elements, like from 118, don't actually exist. Like they can't exist. So then why do we keep space for them if they're never actually going to exist? And if we're keeping space for them, why not keep space for like the ones beyond 118?
Oh, we definitely do have space for them. Beyond 118, like pretty simple. If you had an element that you could study that had atomic number 121, where would you put it? You just create a new row, right? Like the existing system is not going to change. You're just going to have an extra new row of stuff. That's it. So the rest of it is not disturbed. So that is another major advantage with this periodic table, that everything is neatly fitting in its place. And whatever new thing may come to light, this is not going to get changed. It's just going to be another new row. That's it. Okay. And this is so amusing to me personally, because when I was your age, so that was what, 2006 ke pehle, around 2005-6 ke time pe, I had studied that there were 108 known elements. And now when I started to teach, like abhi last 2-3 years mein, is like there's 118 elements. So 10 new elements in the last 10 years discovered. And when I was studying, like 108 tak jo bhi, whichever is grayed out over here, right? So these names were not there. Like the periodic table I used to see, it had like UUN, UUQ, like stuff like that, which was rather weird. But yeah, so now, by now, like IUPAC has decided on names, and you guys are getting these names here, 118 tak. Yeah. Yeah. That's fun. But yeah, so this is like nomenclature. Do you guys want to do like 3-4 of them for practice? Just for the heck of it. Okay. Again, the same thing. Figure out the name and give me the symbol also. Okay. So 117, 124, and 108. So just do it for like these three. हाँ, Arnav, yes. Adit, yes. Symbol भी भेज देना, काम में काम हो जाएगा. Yes, Ritu, the names, you got all of them. Smera, name and symbol. Yeah, you got all of them. Adit, only the first letter is capital. Baki do should be small. Okay. Yeah. Names, pretty much all of you have got it. Absolutely right. So this is unseptium. This is unbiquadrium. And this is uniloctium. Yes. So this is UUS. This is UBQ. And this is Uno. Yeah. Cool. Okay. Do you guys think this is like difficult to remember names ke liye, ye wala table? Pretty simple, logical, like half of it, not even half. Out of 10, almost like 8 of them you're familiar with. Bachpan se you were learning 5 pent, 6 hex, 2 by 3 tri, 4 quad, all of this stuff. Only thing you need to remember is 9 is N, O is nil, 7 is sept, not hept. Okay, that's the only minor thing. Okay, that's one section. Nomenclature ke baad. Okay, so now we'll jump directly into the periodic table. Acha, tell me, you guys, which is better, like visual, like which is good on eyes for you guys, like visually? Is it visible? Is this better, or was the previous version better?
The previous one.
The previous one.
And is this good, or but isme I don't have all of the filters. That's the problem. Okay, we'll talk about this when we just want the plain periodic table. Properties ke saath, this is like ideal. So I'll go with this. Let's see if I can get this. All right, nice. This is good. So now we're getting deeper into the periodic table. First, we'll talk about how the periodic table relates to the electronic configuration. Okay. So before that, we said there are like 4 blocks, right? I said there's S block, P block, D block, and F block. Do you guys like, you must have figured out why the names of the blocks are given like this, like specifically SPDF. So why do you think these are the names?
That's where like the last electron is, like the
Absolutely.
valence shell.
Yes. It relates to the electronic configuration. Wherever the last electron goes, whichever orbital the last electron goes, if it goes into the S orbital, you get that element in the S block. Goes in the P orbital, P block, D orbital, D block, and F orbital, F block. Okay, so that's what they relate to. That's what they stand for. So I'll roughly consider the, let's like look at the properties of S block. So S block, the first 2 groups consist, you have them in the S block. So first property, what do you think is the general electronic configuration for S block? So inner electrons, like as
It ends with S1.
only S1?
It ends with S.
S2 also.
Yeah. So first group may you have S1, like 1 is 2, 2s1 is lithium, 1s2, 2s2, 2p6, 3s1 is sodium. If you look at magnesium, that goes to 3s2, right? So the general electronic configuration is like the valence electrons goes into ns1 or 2. Like pehle noble gas ka configuration hoga, uske baad it ends with ns1 or 2. Okay, so n you can relate it to be the period ka number, like which period it is in. So if it's in the 5th period, so these 2 elements will end in 5s1 and 5s2. That way, you can figure it out based on that. Second property, what kind of elements do you find in the S block mainly?
Metals.
Yes. And what kind of metals are there? Like D block, maybe you find metals, iron, cobalt, and also.
Alkaline metals. Alkali and alkaline metals.
Alkali, alkaline, yes. But what is special about metals like sodium, magnesium, cesium?
You can dissolve in water.
Absolutely, yeah. That is one property. So they form, like the elements all form soluble bases. But again, like if I say sodium, what's the first thing that comes to your mind?
It's soft.
Correct. So the striking thing about these the elements of S block is that they are extremely soft metals like sodium, potassium, magnesium. You can cut them with a knife, you can just like bend it and then it can break apart. Also, what is special about these kind of metals? Like you are familiar with sodium, potassium, cesium, magnesium. They are extremely reactive, like violently reactive metals.
Highly reactive in nature, as they
So you find soft, extremely reactive metals. There are also elements that form soluble bases. We discussed the electronic configuration. What else do we talk about? Yeah, the soft matlab, you can relate this to the fact that they have low melting point, boiling point. They're highly reactive. Again, we kept saying repeatedly they are all metals, so they're like highly electropositive metals. They can give away electron easily, which again relates to their extreme reactivity. And final thing, yeah, they're strong reducing agents. How much you guys remember about oxidation reduction, what it means, all of that stuff?
Oxidation is basically the addition of oxygen and the reduction of hydrogen, and in reduction it's basically you add more hydrogen and oxygen is
Removed. Okay.
You've given us like the oil rig thing. I remember that by.
So that is specific to electrons. So like, what is it in terms of electrons?
So oxidation is loss and reduction is gain.
Reduction is gaining.
Electrons.
Correct. So if something is gaining electrons, it is getting reduced. And if something is losing electrons, it is getting oxidized. So related to that, how would you identify oxidizing agents and reducing agents? So agent ka matlab something that will help with or something that enables oxidation or reduction. So yahan pe we're specifically saying, yeah, go ahead.
I'm not very confident, but like would reducing agent be like it's ready to give one electron, so whoever it's reacting with would gain one?
Absolutely, that's it. So reduction is gain of electrons, right? So gain kahan se ho raha hai? If something else is ready to give electrons. So that's something else that gives electrons so that the reduction can happen. So that's a reducing agent. Now, because these S-block elements, they can give electrons quite easily, they form really strong reducing agents. Yeah. Cool. So abhi se, try to get familiar with figuring out oxidation reduction in terms of electrons, because that's what we'll be dealing with now. Or just be familiar with it. You have a whole chapter on redox reactions where we're going to get in detail. Okay, so these are the properties of S-block elements. So once you've noted them down, we'll be discussing properties of P, D, F blocks also in the same format, or like similar points we'll be touching on. Okay. So let me know once you're done, and then I'll make space. We'll discuss P block.
Ma'am, what does low MP and BP stand for?
Oh, MP is melting point, BP is boiling point.
Oh, okay.
And this is electropositive. मैंने E minus डाला है. You can write electropositive. Okay. Ritu, Smira, you guys done? Okay. Done. ठीक. All right. Next, we'll go with P block. तो पहला point क्या बोला था S block में? Electronic configuration. तो P block के लिए क्या होगा? So valence shell का electronic configuration क्या होगा?
NP 1 to 6.
Yeah. So NS2 and NP 1 to 6. So whenever we talk about general electronic configuration, right, we talk about the whole valence shell ka configuration, not just the last orbital ka. Yeah, that's the thing. So all of them, they have completely filled s orbital. Uske baad 1 to 6 boron se neon tak all of this. Okay, next S block mein we saw there were soft, really volatile metallic compounds there. Volatile, really reactive metals in S block. P block mein what kind of elements do you find?
They're all gaseous.
They're all gaseous.
Noble gases.
Noble gases hai. Other gases bhi hai. You have oxygen, you have chlorine, you have fluorine.
Non-metals.
Halogens.
You have
and
non-metals, yes. Do you find only
Halo-
non-metals?
Metalloids as well.
metalloids also.
Metalloids also. And then what about things like aluminium, gallium, tin, lead?
Metals as well.
Metals also. So P block has the most diversity. You'll have metals, non-metals, and metalloids. Okay, so you have like, yeah, very like lots of different elements here. So in case of P block, we can't generalize the the way we talked about S block, that they are low melting point, high melting point, like that way we can't generalize because you find all different kinds of elements here. But one thing you can generalize compared to other blocks, P block is usually characterized by high electron gain enthalpy. And high ionization energies. Yeah. So compared to like, it's not that they have high electron gain enthalpy full stop. It's more like compared to all other blocks, you'll find the highest electron gain enthalpies in the P block and highest ionization energy in the P block. Okay. And finally, another point we talk about is that the oxidizing nature in the P block elements, it increases as you go towards the right. So like these elements are, I mean, situationally, obviously, a lot of them can be good reducing agents also. Like you consider aluminium, it's one of the highly reactive metals. It tends to reduce other metals rather than oxidize. But as a general rule, like beyond 1 2 exceptions, usually these are characterized by their oxidizing nature. They form good oxidizing agents. And it increases as you go on the cell. Yeah. So again, it's very difficult to generalize P block apart from the electronic configuration because it's got like such a diverse kind. Like you have the most reactive, like least reactive, both ends of the spectrum here. You have all different metal, non-metals, metalloids, everything. So.
Ma'am, what's the meaning of enthalpy?
Enthalpy is like a word for energy. It's a very specific form of energy, like energy calculated in specific situations. We'll get in depth about it when we do thermodynamics, which is all about like energy related calculations. But for now, you can think of enthalpy as a form of energy only. You can. In fact, this also, like if I have to be accurate, I should say ionization enthalpy rather than energy. But yeah. Generally speaking, it's the same thing. Enthalpy also measured in joules. They stand for the same thing. But if you have to get really technical about it, it's a form of energy calculated in a very specific situation. Thermodynamics, maybe get into it. There's like internal energy, there's enthalpies, there's heat versus work done. Like depending on the situation, you use a different word for it. Yeah. Let me know when you're done, Arnav. Ritu, are you noting down or are you done?
I finished noting down.
Now comes D block. D block, there's like quite a bit to talk about it. But first, let's start with the electronic configuration. What would be the electronic configuration of D block? You can consider any random element and then figure it out.
NS2D 1 to 10.
NS2. NS.
NP6 and 1.
Yes, 0 to 2.
Look at it over here. I've selected a D block element so that you can take hint from it. NS, okay. NS, okay, what happened in the case of like chromium or copper?
It was N1. I mean S1.
Right? So it can be NS1 to 2 depending on the situation. उसके बाद NS के बाद NP fill हो रहा है कि कुछ और fill हो रहा है? Like 4s2, 5s2 के बाद, which shell are you filling? 4s के बाद?
3D.
3D, right? So what comes after NS1 to 2?
N minus 1D.
N minus 1 D 1 to 10. Okay, so this is the general electronic configuration. So NS usually, ideally it should be 2, but due to weird cases can be either 1 or 2. Uske baad the previous shell ka D, this thing is being filled. So another way to write this, like if you do a random Google search, you'll find it written in order. So sometimes you can also say it's N minus 1 D 1 to 10 and NS 1 to 2. ऐसे भी लिख सकता है. Order of filling is first S and then the D, but like denoting it can be denoted either way. Either the order where it's filled or in the order of like sequential order. Okay, so D block elements are also, they have a special name. They're called transition elements. Why do you think they're called transition elements?
The table is transitioning from metal to non-metal.
It's more transitioning from S to P. Not necessarily non-metal, right? Like P block में भी यहाँ पे पूरा metals ही आ रहे हैं ऐसे. Polonium is also metals. So yeah, यहाँ पे पूरा ऐसे metals है. So it's not necessarily metal to non-metal, transitioning from S to P. They form the bridge between S and P elements. And in true fashion of like mediums, they show characteristics of S block as well as P block. Like for example, S block jaise, they are mainly metals and they have valency 1 or 2 mainly. P block jaise, they are capable of forming covalent bonds. Like the empty d orbitals that are there, they allow other electrons to share. Like chemical bonding, we've come across stuff like dsp2 hybridization and d2sp3 hybridization, right? So this kind of hybridization is shown only by d block because they have these empty d orbitals there. And the empty d orbitals, they take part in something called coordinate covalent bonding. So that way they're like the bridge between S and P. Okay. What else can you say about these elements? Like S block had all metals. Isme you have metal, non-metal, metalloid. D block may what kind of elements do you find?
Only metal.
They're all metals, yes. And S block was violently, like extremely reactive metals. D block, you will find. What can you say about their reactivity?
It decreases as you go, right?
They're in general moderately reactive. Okay. Decreases, again, it depends. Like this particular set, copper, silver, gold are outright not reactive. But again, zinc is more reactive than copper. So it depends on a lot of situations. Like you have the half-filled state, fully filled state, like all that stuff coming in. So, but D group, D block as a whole, they are moderately reactive. They're all metals. So S block had metals that had low melting and boiling points. D block has metals that have high melting and boiling points. That's the difference between S block and D block metals. Okay, and then we'll talk about 3 more properties that are very specific. They're special to only D block. Maybe S block will also, not F. F block also will show these properties, but D block is known for it. Like if you think of these properties, you would associate it only with D block elements, kind of like that. The first property is they form colored compounds. That is because the ions itself are colored. So when you have a specific ion like ferrous ion or ferric ion or cuprous ion, specific ions have specific colors, like they form colored ions, which ends up, like you can see that their compounds that have those ions are also colored. Do you remember some of these colors? Yeah. Which ones do you remember, Ritu?
Copper was like reddish brown.
Huh? No.
And
Copper metal is reddish brown, but ions like copper compounds are what color? Oh, that you don't remember. So copper has like brilliant blue color. Like there's a post also online. So copper forms like all shades of blue, from like a royal navy blue to a teal kind of blue to a light blue. Like different copper compounds have different shades of blue. Iron is pretty popular. Like if it's a ferrous, like 2+ state may it's green in color. If it's a 3+, then it's red in color. That's why your rust is like reddish brown in color. Manganese forms purple, like potassium permanganate is purple because it has that particular manganese. And then the purple color disappears when that manganese is that's reduced. KMnO4 it's in +7 state when it is reduced. What others? Zinc is
gold is like shiny yellow.
Gold metal is shiny yellow, yes. But gold compounds are red in color. Yeah, if at all you come across, like you mix gold in aqua regia, that solution becomes like a pinkish red in color. So gold atoms are pinkish reddish, that kind of shade. So like these are like the popular ones. I forget. Chromium, one specific ion of chromium is a bright orange color. Yeah, dichromate is like really bright orange. So yeah, so different, like D block is known for, like if you have a colored salt, it means it's a D block ion. Actually, have you guys done practicals this year yet? Do you have them? No? Oh, okay. In case you do, you'll have something called salt analysis, like qualitative analysis here. You'll have titrations and you'll have salt analysis. Salt analysis is like you'll be given an unknown salt and then you have to figure out what salt it is, like what is the cation, what is the anion. So all of these things, color of different ions, and then you have like specific reactions, and then it gives like a specific color and all of that stuff. So that's salt analysis. So that's one thing. Another property of D block elements are they show something called paramagnetism. What do you mean by paramagnetism? Or paramagnetic, diamagnetic? No? So, before we go there, Ritu has asked a very good question. Ion and metal are completely different. So, yeah, the element is the same, but how are ions formed?
You add or remove an electron.
Correct. So now, since we're talking about D block elements, usually they have tendency to lose electrons, right? So ions usually have a stable configuration, not necessarily octet, like X block and P block form octet ions, but D block they just tend to lose the S electrons, or sometimes they tend to lose like all the D electrons depending on situation. So that's another property of D block, is that they have variable valencies for that reason. Now, when they lose electrons, the electronic configuration itself is changing, right? And because of that, one, they are attaining charge, like a positive charge. So ions are not capable of existing independently. So either you'll find them in solution or you'll find them in salt. Like they always attract the negatively charged particles from wherever they can get. So yeah, ions don't exist independently, but metals are capable of doing that. And secondly, when an ion is forming, the electronic configuration itself is changing. And all these properties that we're talking about, colored ion, their magnetic properties, all of that comes from the electronic configuration because of the fact that they have a specific kind of electronic configuration. So many unpaired electrons, so many paired electrons, all of that. So that is the reason when we talk about these kind of properties, it's important to figure out if it's a neutral metal, which has not lost any electrons, or if it's an ion. So that gives you an idea of how the electrons are arranged. Okay. So when we're talking about paramagnetism, so this you'll find it like most relevant to what we're talking about. So paramagnetism is the reaction to a magnetic field. Okay. So what happens when you place any element in a magnetic field, element or an ion, any atom in a magnetic field, is that one, either it is attracted to the magnetic field. The thing about magnetism is we don't know why magnetism happens. Like, we know the effects of it, the consequences of it, but why does that happen is still something that researchers are figuring out. Like, humanity doesn't know about it yet. So what happens, like the effect is that when you place anything in a magnetic field, the electrons, like different electrons have like different spins, right? So all the electrons are aligned in a single direction, like either towards the magnetic field or away from the magnetic field. They're affected by the magnetic field. So the spin of electrons is what the magnetic field interacts with when it comes to metals or materials behaving in magnetic field. So paramagnetism is when the element is affected by magnetic field, and diamagnetism, it's the opposite of paramagnetism. Diamagnetism is when it is completely unaffected by magnetic field. Okay. And apart from these two, there's something called ferromagnetism. So ferromagnetism is basically paramagnetism on steroids. Like, at least I call it that. So paramagnetism is the fact that that element is affected by magnetic field. Ferromagnetism is the effect is so extreme that it behaves like, how iron does with magnetic fields. Like, if you bring iron close to a magnet, you can literally see it getting attracted, right? Iron sticks, or magnet sticks to iron things. So that kind of property where it's completely visible, so that's ferromagnetism. Okay, so it's the extreme attraction to magnetic field. Paramagnetism is there is attraction to magnetic field, there is a reaction to it. And diamagnetism is when there is no reaction to magnetic field. So this, whether something is paramagnetic, diamagnetic, or ferromagnetic, or for now we'll only consider paramagnetic or diamagnetic. So this depends on the number of unpaired electrons. I'll just write in a whiteboard because it's easier. So magnetic properties depends on the number of unpaired electrons. So unpaired being the keyword. Okay. So let's say you have a partially or incompletely filled orbital, d orbital. So then you have 1, 2, 3, 4, 5, 6 electrons. Now out of these, 4 of them are completely unpaired, right? So all of these, now because you have 4 unpaired electrons, this particular element is going to be paramagnetic. Okay. And it is possible, like there is a physical, like you can calculate what is the magnetic moment also. Basically, like how much is the effect of the magnetic field. So that's called magnetic moment. How much is it going to be affected? So that is root of n into n plus 1, I think. N plus 1 or n minus 1, I have to calculate. So let me just clarify it. But yeah, where n is the number of unpaired electrons. So greater is the number of unpaired electrons, more is your magnetic moment going to be, like its effect to magnetism. Now, if all of the orbitals was completely filled, if there was no unpaired electrons at all, the electronic configuration was something like this. Then this has 0 unpaired electrons. All the electrons are paired up, which means that the magnetic moment is going to be 0, which means that it is not affected by magnetic field. And not affected matlab this is going to be diamagnetic. Okay. So paramagnetic is the fact that it is affected by magnetic field, and diamagnetic is if it is not affected by magnetic field. And whether it's paramagnetic, diamagnetic, you just have to look at the electronic configuration and you can figure it out. So all the electrons are unpaired, then, I mean, if you have at least one unpaired electron, it's going to show paramagnetic nature. And if all the electrons are paired up, if there's 0 unpaired electrons, then you can say that it's going to be diamagnetic. Okay. So d block elements, because they have d orbital, they are going to be especially paramagnetic. Now you won't find that, like we don't talk about magnetic quality of S or P block elements. This, it makes complete sense. Like you can figure it out easily. S orbitals may, how much is the scope for having unpaired electrons? Like S orbital may maximum kitne electrons ho sakte hain?
2.
2, right? Which means that the only possible configurations, either you have S1, which has 1 unpaired electron, or you have S2, 2 unpaired electrons. Yeah. Next, if you look at P block elements, S is completely filled, that's is paired up electrons. P may, you just have 3 orbitals. So the maximum extent you can go is like up to 3 unpaired electrons. Otherwise, you just have 1 unpaired or 2 unpaired. Usme bhi, you can see that some of the elements, they form compounds. So again, all the electrons are paired up. Like nitrogen, if it existed as N atom independently, then we can think of maybe there's like unpaired electrons, but it is forming N2 molecule, which means that the electrons are all eventually going to be paired up, right? So that is why S and P block may you won't come across paramagnetism so much. The scope for magnetic moment is like extremely low. In the case of D block, you have empty d orbitals, which can take up to 10 electrons. So you can have between 1 to 5 unpaired electrons. That is the reason you talk about paramagnetism specifically in D block elements. Okay. And the other property that we talked about, the fact that they form colored compounds. So the color also, you can perceive those colors when the electrons are basically jumping from one d shell to another. You have constant excitation and de-excitation, right? So that happens, like when that happens, when electrons are excited and then they jump back. So when these, you call them DD transitions. So when these DD transitions occur, electronic transitions, that's where it gives off energy, which you can see it as visible light. That's why they form colored compounds. Yeah. Just a moment, you guys, I'm getting a call. Sorry about that. Okay, so one is magnetism, then we have colored ions, and another property, variable valency. So the variable valency is also because, they have d orbital. Like in the case of S, because it goes only up to 2 electrons, it's easy to lose 1 or 2 electrons. In p block also, it's easy to just gain whatever is the required number of electrons, or you just form like a covalent compound. But in the case of d electrons, like d block elements, you have like their valence shell has ns1 2, and you have n-1 d1 to 10, right? It's difficult to lose like 7-8 electrons at a stretch. It makes it really, really unstable having that big of a charge. So that is the reason d block elements settle for the next best thing, which is losing the most outermost electrons, their s electrons. That is why you will find that a lot of these compounds show a +2 valency. We call it a +2 oxidation state. Copper specifically, because that has ns1 that shows Cu +1. And apart from that, they lose how many ever d electrons, like how many ever it makes sense for them to lose. So for example, if you look at iron, what is the atomic number of iron? Who remembers?
26.
26. Electronic configuration of iron? You don't have to say the whole thing, like the compact form you can say. Argon, 18 electrons यहाँ तक हो गए. उसके बाद
Four s2 d6.
yes,
3d6.
3d6, right? So iska matlab you have first, okay, like if you look at the iron atom, inner electrons are completely filled, they're not going to be bothered. The ones that take place in bonding are the incomplete ones, which is going to be the 3d orbital. So you have 1, 2, 3, 4, 5, 6, and the 4s2 electrons. So when iron loses these 2 electrons, then it shows the oxidation state of Fe2+, the ferrous ion. What is the next best thing that iron can do? Like iron cannot lose all 6 electrons. So what is the next most stable configuration iron can aim for?
It loses the 1 electron it has, so it becomes d5.
Yes. So then like agar fully filled octet configuration possible nahi hai, so then it is going to go for the next best thing, which is half filled configuration. Do you remember half filled is stable? So it has a perfectly half filled configuration. D5 milega on losing this single electron, and that's when it forms Fe3+ ion. So that is why these are the 2 possible oxidation states or valencies for iron. Okay. So that's why based on the, that is the reason D block elements have variable valency. So one valency, definitely you get it by, or they get it by losing the s electrons. And the other valency, other 2 or 3 valencies is based on whatever is the most convenient for that particular element. So it could aim for the half-filled configuration like iron, nickel, all of that. Or if it's like if it's D1, D2, D3, then it loses all of the D electrons to get that particular valency that way. Okay. So variable valency is one of the property. specific to D block. And paramagnetism, we've spoken about it. And another thing about D block is that a lot of these elements act as catalysts in a lot of reactions. So whenever you see that a reaction requires catalyst, more often than not, it's going to be a D block element. Like nickel is a popular catalyst in hydrogenation. Palladium, platinum are also used, like this whole group is like a popular catalyst. Iron is used as a catalyst in manufacture of ammonia. Yeah. So that way, a lot of D block elements act as catalysts. Okay. So these are all the properties of D block. So just to summarize it, so we discussed the configuration of valence shell for D block elements, n-1, d1 to 10, ns2. They're also called transition elements because they basically form the bridge between S and P electrons. S and P blocks. They consist of all metals only, having high melting and boiling points. S block is metals but low melting and boiling point. D block is metals, high melting and boiling points. They form colored ions because incomplete d orbitals. They also show paramagnetism because unpaired electrons in d orbitals. And they show variable valency because they can lose the 4s electrons and 3d electrons. And these metals or these elements are mainly used as catalysts. So you have good reducing agents on this side, you have good oxidizing agents on this side, and you have catalysts in the middle. Okay. Next, let's look at F block elements. Again, just like always, configuration of F block. Hamesha start with like you are going to have NS2. NS2 के बाद क्या fill हो रहा है?
n-2f.
हाँ. NS के बाद you have yes n-2f और f का range क्या है? Adat, I think I'm not able to hear you. Are you muted?
No, I'm muted.
Ah.
Yeah.
Then
Will it be 1 to 14?
correct. F can take 14 electrons, so F electronic configuration will range from 1 to 14. Just like D block may you had S1, right? So in this case also, because of some weirdness, you will have NS12 and also N-1D 01. A lot of times it is 0, but you have like some exceptional cases where the F electron goes back into the or goes into the D shell. Or to denote it properly, you can say सबसे innermost shell is N-2F 1 to 14, then N-1 D 0 to 1, and उसके बाद NS1 to 2. So this is like the sequential inner to outer. This is like the order of how it enters the electrons. or how the electrons enter. Okay. F block may you just have like 2 rows of elements. What are the names of these two like groups of elements or bunches of elements? इनका नाम क्या है? F block में
Lanthanides and actinides.
lanthanides and actinides. Actinoids बोल सकते हैं, actinides, lanthanoids or lanthanides. Yeah. In this group also you find all of them are metals. The way we had lots of special points about D block elements, F block may you just have like 2 points, 1 point actually. So actinides are all radioactive. They're all radioactive. And a lot of them are also like uranium se leke, they're synthetic. Yeah, not all of them are synthetic. All of them are radioactive. After uranium, they're mostly synthetic elements. And again, just like D block, F block also show like there are many oxidation states possible, like variable valency basically. So many oxidation states are possible, the most common being +3. So +3 matlab they lose 2 of the s electrons and then a lot of them lose 1 more electron. Yeah. Yeah. Ritu, Smira, you guys done? Awesome. Okay, so we went block by block. Acha, before I go further, are you guys aware of like what do you mean by oxidation states? Have you come across that word earlier? No? Okay. So oxidation state is like similar to valency. The meaning is given here, quite convenient. So oxidation states, it indicates the number of electrons that are added to or removed from an element when it forms a chemical compound. So it gives you an idea of is it likely to lose electrons or gain electrons. So even if the compound, if it's forming a what do you call a covalent compound, like let's take for example HCl. HCl is covalent, right? Like both are non-metals. The electrons are shared between them. But do you think the electrons are shared between hydrogen and chlorine equally? No. So who has a more of a better hold over the electrons, even though they are shared? Chlorine would have like a better hold over the electrons. They are not shared equally between hydrogen and chlorine. So to give that information, we say that chlorine has an oxidation state of -1 and hydrogen has oxidation state of +1. So even though we are indicating +1, -1, it doesn't mean that it's an ionic compound. It is just showing that chlorine is likely to gain the shared pair of electrons and hydrogen is likely to lose the shared pair of electrons if you were to break this bond. And also the fact that even if HCl was together, the shared pair of electrons is going more towards chlorine and less towards hydrogen, something like that. Okay, that's like a brief idea of oxidation states. So in redox reactions, this is going to get even more important. It will help you figure out if something is getting oxidized or reduced. So if oxidation state increases, it's oxidized. If oxidation state decreases, it's reduced. And you have a whole system of how do you calculate oxidation states, like potassium carbonate make carbon co-oxidation state, yeah, like stuff like that. Cool. So that's like a brief, like you have basically studied a rough notes about every single element you find in the periodic table. So if I pick any random element, let's say osmium. Now, osmium is something that you guys are not familiar with. You haven't come across any osmium compound or anything at all. But now you can talk about osmium. So can you give me some of the rough properties of osmium?
It's a metal.
It's a metal. Is it like
Moderate.
a moderately reactive? Yes.
It will have
High melting point.
melting point and
Colored ions. They will have colored ions.
Osmium will have color.
It's paramagnetic.
Could be paramagnetic. Yes, absolutely. You like Arnav and Smera talked about melting point, boiling point. Like, what about their melting and boiling point?
it will be
It's high melting point.
High
It will be high.
melting boiling point. Yes. Okay. So already you have a good idea. Like you know that it's not going to be like sodium, potassium. Yeah. So yeah, that's how you use the periodic table. Like if you know the position of it, you can get familiar with it. You know what direction to take it in. So if we talk about cesium, now would you, knowing that cesium exists over here, are you going to be careful handling cesium, or are you going to be like, it's okay, I can touch it with my hand?
Careful.
Careful.
You have to be careful because it is among the elements that are highly reactive. So you don't know how cesium is going to be. Yeah? So that's kind of how you use the periodic table. Okay. Californium exists over here. Is it radioactive or not radioactive?
It is radioactive.
It is radioactive.
It is radioactive. Yeah, like that. Cool. So that's like a rough idea of the whole of periodic table. Now we know that we just said cesium is likely to be reactive, but how reactive? Is it going to be more reactive than sodium, potassium, or less reactive than that? So if you want to get into that much of a detail, we're gonna talk about the periodic trends. You know, how do these kind of properties change when you go across a group and, you know, top to down in a group or across a period, things like that. Before that, you have another bit about figuring out the electronic configuration based on the position in the periodic table, right? Okay. Do you like, I just pointed out a random element. Okay, let me point out a different element. I'm not going to click on it. Do this. SB hai, it's antimony. Its position is over here. Can you figure out what is the electronic configuration of antimony based on the position? Okay. So can you send the electronic configuration over chat? If you guys think you're not able to do it, if it's stuck, if it seems a little too complicated, let me know, I'll discuss it. But if you think you can do it, yeah, send it over chat. I'll check. Actually, before you send the electronic configuration, does your school accept the short form of configuration? Like if you see on the left hand side, configuration is given by giving the noble gas configuration and only the valence shell. So does your school insist on you writing the expanded form only, or if this is this accepted? Don't know.
We have no idea actually.
Acha.
Yes.
Because if they accept the short form, nothing like it. That's really, really convenient. At least if you
I
have.
think they do because one time I answered with that and like the chem teacher didn't say anything. So I assume it's okay.
Okay. In that case, you guys can send me the short form only. Chalega. Because if you have to start from 1s to 2s2, it's going to be a little time consuming. Oh. Adit, यहाँ पे 4s2 के बाद you send 4p6. Whenever you're sending the short form of it, right? So it follows a specific pattern. So हमेशा short form, you first indicate the noble gas configuration to show that वहां तक all the orbitals are filled, and then you write down the remaining configuration. Okay.
So you can't take it from anywhere in between.
No, you can't take from a random position. Always it starts with the previous noble gas. Okay, like if you have antimony, the noble gas you get just before antimony is krypton. So you write Kr like this in square brackets. Uske baad, this indicates that Kr ka configuration hai. Matlab yahan tak all the shells are filled. And then you start off, whatever is the next bit of it. Okay. Adit ke baad mera sent. Okay. The ordering of it is a little off, Smira, but yes, you got it. Ritu, yes, you got it. Arnav sent, yes. Adit, you're again, like it is correct, just the order is different. Okay. Awesome. You guys got the hang of it. So you just blindly follow the periodic table. So again, as I said, noble gas just before antimony is krypton, square bracket. Krypton ke baad starts with this. So what does this represent? So fifth period hai 5s2. So 5s1, 5s2. Uske baad aayega n-1 hamesha. So that's 4d, all 10 are filled. So 4d 10. And then yahan pe p block chalu hai. So it's 5p1, 5p2, 5p3. You guys pretty much got it. Absolutely. Yeah. So if you look at the periodic table, you can see that you just count the number of elements and that's going to give you the electronic configuration. So it's like 1s1, 1s2, then 1s ke baad 2s start ho raha hai. So 2s1, 2s2, 2p1, 2, 3, 4, 5, 6, and 3s, then 3p, then 4s ke baad 3d fill ho raha hai. So this will outright give you the order of how the table or how the orbitals are filled. So the table literally is giving you the electronic configuration also. Okay. only minor things it's not directly clear from the table is the anomalies like copper and chromium, like jahan pe bhi, like in this case, instead of 4s2 3d4, it changes into 4s1 3d5. So that you need to be like aware of. So if you notice that jahan pe bhi half filled aa raha hai, all that you need to be aware of, but otherwise you can get the electronic configuration. Yeah, awesome. We have one more hour, and the only thing pending is the trends of the properties. What all properties do you guys have? We'll talk about radius. We'll talk about ionization enthalpy. Then we have electron gain enthalpy. Then we have electronegativity and metallic, non-metallic character. Awesome. Okay. So you guys want to take like a 5-minute break before we start with the trends? Yeah. It's been a lot, right? Okay, yahan tak. Now, how do you guys feel? Like, is it better? Periodic table, are you able to read it better? Kya ho raha hai?
Yes, ma'am.
Yes, ma'am.
First is the atomic radius. What do you mean by atomic radius?
The distance between like the valence shell and the nucleus of the atom.
Absolutely. Like from the center to the valence shell. Distance, that distance, radius of the atom basically. Yeah, we got it. So that's atomic radius. Is it possible to measure atomic radius? Like, do you have any device that measures atomic radius? Like, do you have like a tiny scale that measures in terms of nanometers or picometers? No, right? So the way you measure atomic radius is through spectroscopic studies. You can figure out where all atoms exist. So basically you blast some light at it, like X-rays or whatever. And then based on the results and the readings, like based on the atomic spectrum and all that, you can figure out, there are ways to figure out or detect the presence of atoms, like how closely they are located, how far away they're located. So once you see that there are two consecutive atoms located, using the distance between those atoms, you can figure out the radius. Now, all atoms are not the same, right? You have solids, you have liquids, you have gases, you have ionic compounds, you have covalent compounds. So based on that, you have 3 different measurements of radius. One, you have something called the covalent radius. Then you have the metallic radius. And you have van der Waals radius. Clear. What do you mean by covalent radius? No idea? Okay. So covalent radius, like if I had to tell the exact definition. So it is half of the internuclear distance Now, internuclear distance, basically half of the distance between 2 nuclei. Now, what kind of nuclei? So half of the internuclear distance of combining atoms or of atoms, let's call them identical atoms, of identical atoms that are covalently bonded or that are in covalent bond. Okay, so let's dissect this now. So covalent radius is half of the internuclear distance. Kiska internuclear distance, not any two random atoms. You take two identical atoms and you see that they are in covalent bond with each other. So you measure the distance between both of them and then you take half of it. Okay. So covalent radius, like if you are taking measuring the radius in the situation of covalently bonded atoms, that is the reason it's becoming a covalent radius. Now, another important term in this is the fact that you need to take identical atoms. So this means that if you measure covalent radius, it is going to be for species like O2 or Cl2 or H2 or N2, things like these. If at all you consider HCl, are you going to get an accurate result? No, because there are two different atoms, right? So if you take half of it, you just get the average distance between them. Also, you'll be confused, like, is that supposed to be H ka radius, Cl ka radius? It doesn't make any sense at all. So in order to calculate the radius in this way, it needs to be identical atoms like oxygen, chlorine, hydrogen, these kind of species. So when you have two identical atoms that are covalently bonded, it's going to look something like this. You can detect that there are two atoms here. You can detect where their nuclei are. If you take the distance between these two nuclei, you're essentially calculating this entire distance, right? So if you were to calculate the radius of any one of these atoms, again, both are the same atoms, oxygen ho ya chlorine ho, whatever they may be. So if you were to take the radius of each atom, you need to take half of this distance. So yahan se yahan tak you get the radius of any atom. Okay. So this is what this half of, you're taking one half of the distance between both these nuclei. So half of the internuclear distance. So that will give you covalent radius. Okay. Okay, clear? Based on this, can you figure out what is metallic radius then? All of them follow the same logic, huh? So metallic radius again is going to be half of the internuclear distance. Now, when we talk about metallic radius, what situation are these atoms in?
Two metal atoms.
Yes. Okay, so you take a solid metal. Now metallic atoms, they're solid, right? So they're all, like all the metal cores are tightly arranged, packed this way. So you take any two adjacent metal atoms and measure the distance between them and take half of that. Yeah. So it's half of the internuclear distance separating two adjacent metal cores, you can say, like separating the metal cores in a metallic crystal. Okay. So solids may, the way the atoms are arranged, it's called a crystal structure. Any solid, you have a crystal structure. So in the case of metals specifically, remember I told you that, you have the atoms and then the valence electrons are all like floating around them. So if you take away the valence electrons, like the nucleus plus the inner electrons, this is called a metal core. So you look at any two adjacent metal cores, calculate the distance between their nuclei and take half of it. You get the radius of a single atom. So of course, just like the way you have like metallic radius may, you usually use this method to calculate radius of metals. Sodium, potassium, iron, copper, gold, things like that. Okay. And then finally you have van der Waals radius. Let me know when you guys are ready, then we'll do van der Waals radius. Okay. Done? Adit done? Arnav? Awesome. So van der Waals radius, you mainly use it in the case of noble gases. So basically, wherever it's not possible to find a covalent bond between them, or if it's not a metal where the atoms are close by, adjacent to each other. So when this is also not possible, when this is also not possible, that's when you go with van der Waals radius. So van der Waals radius is half of internuclear distance Now, what situation could these atoms be? So half of the internuclear distance of two identical non-bonded isolated atoms. So they need to be identical. That's when you get the correct radius. And they are non-bonded. Like if they happen to be bonded, it's a covalent radius. So if they're non-bonded, then they're van der Waals radius. Isolated atoms. Yeah. So the situation here is, now if you take noble gases like helium or neon, for example, they don't form any covalent bond. You don't find it as He2 or N2 or something, right? Maximum, these atoms are existing freely. You figure out, okay, what is the closest distance they can get, and you calculate the internuclear distance between the nucleus, and you divide it in half. It's half of the internuclear distance. So that's how you get van der Waals radius. And because of the way you're calculating it, of course, this is not going to give you like an accurate picture of the radius. It is going to be slightly larger because you can't get the atoms any closer than that. Yeah. So it's going to be like extreme. It's larger than what the radius could be. Okay. So all of these internuclear distances, they are measured by spectroscopic methods. So they're measured by X-ray or like this is practically measured this way. Okay. Now I'll ask you guys a question based on this. So now that you have an idea of what covalent radius is or how these three different radii are measured, can you figure out the order of the radius, like which would be the smallest, which would be the greatest? Out of
The greatest would be like van der Waals.
yes, greatest is van der Waals. So if I call this, let's say A, B, and C, what would be the order of the radii? ABC, BAC, CBA, like. So largest is van der Waals, you figured it out. Now between metallic and covalent, okay, Ritu has sent in her answer. Yes, that is right. Anybody else wants to give it a try? सबसे छोटा कौन सा होगा कोवैलेंट और मेटालिक में? Wait, hang on. Ritu sent. Okay. I will have to check if that is right. Metallic covalent. Ah, no, Ritu. Like Adit, the one that you sent is right. I forgot to take one thing into consideration. Sorry. Adit is actually right. Arnav, Smera, you guys want to give it a try? Any idea? No? Yeah. Smera is sending. Yeah, Smera also got it. So the smallest is going to be covalent. Slightly, it's comparable to metallic. So covalent is only slightly smaller than metallic, and you can see. So yeah, both of them are adjacent. So covalent may the atoms are bonded, right? So there's orbital overlap, if you guys remember, right? And metallic may the cores are adjacent to each other. In between, there's like sea of electrons and all that. So because of that tiny difference, covalent is going to be slightly smaller than metallic. But both of them, their orders are comparable to each other. And these two are much, much smaller compared to van der Waals. Van der Waals is going to be really, really large. Okay. So this is the order of the radii. So covalent less than metallic, a lot less than van der Waals. Okay. Okay, so now that we have an idea of what atomic radius is and how it is measured and all, let's get down to the business of periodic trends. All right, should I go to the next page? Okay. Adit? Noting or can I flip? Okay. So consider the trend. So before we get into the trends across a period and from top to bottom in a group, there are a couple of things that you guys need to be familiar with. So one is shielding effect. So have you guys heard of this term, shielding effect? It's also sometimes called screening effect. What is it? Right? It is literally what the words are saying. Okay. So what happens is nuclear has center mein surrounded by electrons, and electrons, how they are arranged, you have like first shell ke electrons and second shell ke electrons and third shell ke electrons, right? So what happens is the inner electrons can basically screen or shield the outermost electrons from the pull of the nucleus. Okay. So effectively, if you consider kitna hold hai nucleus ka on the outermost shell electrons, it is fairly less because there's like a whole wall of electrons in between. So that effect is called screening effect. So because the hold of nucleus is screened by the inner electrons, some of the properties like their ability to form ions, like losing electrons, and all of that is affected. So, and how much the nucleus is pulling on the electrons, that part is also affected. So that effect where the inner electrons are screening the effect of the nucleus, or the attraction of the nucleus from the outermost electrons, that's called shielding effect. Okay. If I had to give you the definition, okay, the electrons of inner shells, also called core electrons, shield or screen the outermost electrons from the attractive pull of the nucleus. That's called shielding effect. The inner electrons shield or screen the outermost electrons from the pull of the nucleus, or let's call it attractive pull of the. So this effect is called shielding or screening effect. You can see why it's called that effect, because there's literally a shielding screening thing happening there. इससे screen कर रहा है from the attractive pull. Okay. And there's another thing called effective nuclear charge. Yeah, लिख लो, then we'll discuss what it is. Yeah. So effective nuclear charge is exactly like what the words mean. Nuclear charge is one thing. अगर 6 protons है तो 6 protons worth of nuclear charge आ रहा है. But if you take away the inner electrons, if the inner electrons are shielding, then you won't get, like, the outermost electrons will not get the full extent of 6 protons ka charge, right? So that way the nuclear charge is slightly reduced. So the effective nuclear charge is like taking into account all these additional things. And for a neutral atom, it will be one thing. If the atom is not neutral, agar ion form kiya, so the relative number of protons and electrons is changing. So then the effective nuclear charge is going to be something completely different. Okay. So taking into account all these situations, whatever nuclear charge is felt by the outermost electrons, like that is the effective nuclear charge. That's all it is. Okay. These are just informations, because when you consider trends, presence will of these may or may not affect the trend. Okay. So now, if you look at the trend, abhi atomic radius ke baare mein baat kar rahe the na. Now, what is the trend of atomic radius from top to bottom in a group? Does atomic radius increase or decrease?
It increases.
Increases, absolutely. And the reason?
Because like more orbits are added and more electrons are added.
Additional shells are added, yes. So at each step, an additional shell is added. So you can see that it's a straightforward increase. Now, one thing to take note of is that the increase is not uniform at each step. Okay, like if you consider a group, so let's go back to the periodic table again. Group may you have lithium, sodium, potassium, rubidium, cesium, right? Let's not consider francium it's radioactive. Lithium to sodium, like har ek case mein you just have one shell being added. Like lithium has 2, then 3, then 4, 5, 6, and all that. Now the increase between lithium and sodium, let it increase X amount. Then sodium to potassium will not be equal to X. It will be slightly less than X. Then potassium to rubidium will be slightly lesser than, like even more less. Then rubidium to cesium, even though there's a new shell added, the increase will not be so much. Okay. So the reason for that is that like when you go from top to bottom in a group, you will observe shielding effect. Okay. So as there are more number of inner electrons, the shielding effect is observed. So you can see here, like lithium is 167, sodium is 190. So difference kitna hoga 167 to 190? Approximately 23.
23.
अभी सोडियम टू पोटेशियम 190 से 243 हुआ. कितना है डिफरेंस? It need not have to be approximate. 50 something, right? Potassium to rubidium 243 to 265.
22.
23, 22.
Is में है. And rubidium to cesium 265 to 298. Again, it's in the 20s. Slightly more than 20, almost close to 30, I think.
33.
33.
30s.
So at one point, the increase, like the difference, the increase in the radius reached almost 50. Uske baad it became like 20, 30. So that irregularity is because of shielding effect. Yeah. So it's not like a regular increase. So group mein you have shielding effect is observed. Okay. Oh, another thing about shielding effect. The shielding effect of S electrons is maximum, followed by P electrons, followed by D electrons, followed by F electrons. So D and F electrons agar hai, तो shielding effect इतना ज़्यादा नहीं होगा compared to S and P electrons. Okay. And that's what you can observe. Like sodium potassium के बीच में there's only S and P orbitals. There's 2s, 3s, right? So इसलिए the jump was like 50 something picometers. When it came to rubidium, like cesium and all of that, वहाँ पे DF electrons भी आ गए. So because their shielding effect is not so much, the nucleus was able to effectively pull the electrons, and increase was again reduced to like 20, 30 के आसपास. Yeah, that is one thing. Okay, now coming to period. So left to right, what happens to the atomic radius?
Decreases.
Absolutely. So left to right, decreases. Reason?
At each step, an electron is added, so due to more electrons, the radius decreases with the pull from the nucleus.
The shielding effect is also lessened.
Proton is also added. So focus on that fact a lot more. Yeah. So proton is added, and the additional electron goes in the same shell. It's not going in a different shell. So the effective nuclear charge on the outermost electron remains this, or it's increasing relative to the number of electrons. So the effect, because of the increased effective nuclear charge, nucleus is able to pull that. Okay, that would be the reason. So if I had to put it in words, you can say, so as there's like more proton and more electron, the pull of the nuclear pull increases. Yeah. And shielding effect is observed, but because all of them are in the same shell, it's the same amount of shielding effect. So, it's not significant, it's not important in this case. You can say like shielding effect does not affect the difference. Yeah. So if we have to explain it in detail, so if you consider sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, all of them are in the same shell. If you look at the electronic configuration, it is varying from neon 3s1 से लेके same neon 3p5 या 3p6 तक, right? So the number of inner electrons is the same, which means that जितने भी protons है, whatever shielding effect is there, that's constant. लेकिन the number of protons, sodium के case में there's 11 protons affecting the outermost electron, affecting the 3s orbital. Chlorine के case में there's 17 protons affecting the same third shell electrons. Yeah. So the effective nuclear charge is increasing as the number of proton increases, and there's not enough, like it's the same number of inner electrons, so the effect of the nuclear pull increases. After atomic radius, there's a tiny bit about ionic radius. So what can you guys say about ionic radius? Neutral atom compared to cation, will the radius increase or decrease when it becomes a cation?
Decrease when it becomes a cation.
Decreases. Like if you compare Na and Na plus, Na has 11 proton, 11 electron. Na plus has 11 proton and 10 electron. So what's happening is the same number of protons, lesser electrons. So protons ka pull dominates. Another way you can look at it is Na ka outermost is 3s1. Na plus mein it is losing 3s1. So the outermost is 2p6. So basically it's losing one whole shell, which is why there's like a drastic decrease in the radius. Yeah. So that's what happens in the case of cations. Two reasons, like depending on the situation. One, due to its loss of like the whole shell itself, and second is the increased effective nuclear charge. What about anions? Like let's say you have oxygen versus
It would increase.
which will it increase or decrease? Come again, Ritu.
It would increase.
It would increase. Yeah, it is the opposite case. Yeah. So again, same thing. Oxygen ke case mein what 8 protons, 8 electrons there. Now it's becoming 8 protons and 10 electrons. So there's going to be like a slight electronic repulsion in the same shell. At the same time, the effective nuclear charge is decreasing. There's less hold of protons over the extra electrons. That leads to the increase in this thing. Okay. Also, if you were to compare, let's say O minus versus O2 minus, which one will be bigger between both of them? Enough.
O minus.
Why do you think that? See, again, apply the same logic. इसमें 8 protons, 9 electrons है, 8 proton, 10 electrons है. तो किस केस में, like, where do you think it will be bigger?
O2 minus.
O2 minus. Yeah. So even if you were to compare between the ions itself, the radius, or let's call it ionic radius, is inversely proportional to the charge of the ion. So zyada charge hai, the smaller will be the ion. So you can use this logic to compare radius of isoelectronic species also. Yeah. So what do you mean by isoelectronic species? Think about it.
They have the same number of electrons.
Yes. Iso मतलब uniform. इसलिए isotopes मतलब same atomic number, different mass. Isobars like same mass number. Isomers like same molecular formula, different structures. So isoelectronic is same electronic species. So if they have the same number of electrons. So if you were to compare Na plus, Mg2 plus, O2 minus and F minus. So इसमें से which is the smallest, like all of them have 10 electrons only, octet configuration. तो इसमें से सबसे छोटा कौन सा रहेगा?
Mg2 plus.
Mg2 plus. Okay. So inversely proportional to charge. charge जितना ज़्यादा होगा उतना छोटा होगा that particular radius. So this is the smallest, followed by
Na plus.
followed by
Na+,
Na plus, yes. Then Na plus will be followed by
F minus.
F.
minus, F minus, okay, be specific there. And that will be followed by O2 minus. So this is going to be the biggest. Okay. Cool. That's it about comparing the atomic size, ionic size. Next, we'll talk about ionization enthalpy. Same as like you guys have learned it as ionization energy because you weren't told about the term enthalpy yet. But now we'll learn about enthalpy. So we start using ionization enthalpy. So what is ionization enthalpy? You also see it denoted as IE. So ionization enthalpy is the amount of energy required. So it's the amount of energy required. So this is a keyword. So it's the amount of energy required for what? So this would be to specifically remove an electron. Even though we call it ionization enthalpy, when you hear the word ionization enthalpy, it's always removal of electron. Okay, so to remove an electron from the outermost shell, so if you are talking about removing an inner electron, then that's not going to be ionization enthalpy. It's not a standard, like you will get an energy value, but that's not ionization enthalpy. It's going to mean something very different. So ionization enthalpy ke liye, you remove it from the outermost shell of a neutral gaseous isolated atom. This is important. So it needs to be a neutral gaseous atom, isolated atom. Okay. So the reason why the definition has a lot of these criteria is because ionization enthalpy, electron gain enthalpy, like all these values mean something. So if you, and they are like standardized values, they are properties of that particular element. And so if you were to compare any of these between elements like ionization enthalpy of sodium versus potassium versus iron versus mercury, you can't, like if one is in solid state, one is in liquid state, you're going to get completely different random values. So अगर कुछ solid में है तो पहले उसको लिक्विड में कन्वर्ट करना पड़ेगा, फिर उसको गैस में कन्वर्ट करना पड़ेगा, उसके बाद वो इलेक्ट्रॉन जाके निकलेगा, right? Because when you heat something, the first thing that happens is like all of these other physical processes are also happening. So if you standardize it, that it is purely the energy required to remove an electron, matlab, you are defining it for a neutral gaseous atom. Then all these other external differences where some energy is going for conversion of physical state, like you're removing all of that. So all these terms are important for that standardization there. So it's the amount of energy required to remove an electron from the outermost shell of a neutral gaseous atom. Okay. So that's when it'll be ionization enthalpy. The factors that affect ionization enthalpy trends will be, so the factors affecting are so you have shielding effect coming into picture. Then you have nuclear charge. You have to take all of this into consideration when you're figuring out the trend. Okay. In some cases, one of these effect factors will dominate. In another case, a different one will dominate. But yeah, you have to take all of this. The third is something called penetration effect. And the electronic configuration. So electronic configuration in the sense, you need to look at, is it half filled, full filled, like that's going to affect how easily or difficult it is to take it out. Okay. So based on this, we'll be discussing the trends. Okay. Yeah. Once you're done writing, I'll discuss each one and then we'll figure out the trend and group and figure. Okay. Ritu and Adat, yes, ready?
Done, ma'am.
Yes, ma'am. Done.
Okay. So, oh, Smira, you still noting down? No, okay. So first thing, screening effect. What do you think the effect of shielding effect will be on ionization enthalpy? So if you find more shielding effect in any case, will the ionization enthalpy be more or less?
More.
Why? So if shielding effect is more, will it be easier or more difficult to take an electron from here?
Easier.
It will be easier, right? तो अगर आसानी से इलेक्ट्रॉन निकाल सकते हो, तो do you need to put in more energy or less energy?
Less energy.
Less energy.
Yeah, so that's why ionization enthalpy will be less. So where you come across this comparison is if you compare S block elements versus B block elements. Now both of them are metals. Ideally metals matlab they can lose electron easily, but S block mein the inner electrons you have completely filled orbitals, like all your sp orbitals, and if there are d orbitals present, they are completely filled. If you compare d block element of the same size, like comparable size, your s orbital is filled, p orbital is filled, but your d orbitals are not completely filled. Like if you want to compare the 3s of this and 3s of this. Okay. So in which case will you find more amount of shielding effect? Let me show you guys the materials. Okay. So compare, let's take potassium, and same row mein you have iron. So potassium mein whatever like इसमें भी 4s electron निकाल रहे, इसमें भी 4s electron निकाल रहे, right? Now potassium में behind the 4s electron you've got the 1s 2s 2p 3s 3p electrons inside. Ion में behind the 4s electron you've got like 1s 2s 2p 3s 3p and some 3d electrons also. Now, in which case will the shielding effect be more, in potassium or in iron?
Potassium?
Correct. Potassium may it'll be more because shielding effect, S and P are able to shield very well. D electrons don't shield very well. And potassium ke andar all the whatever orbitals are there, they're completely filled. The electrons are like happily there. But ion ke case mein, the d orbitals are incompletely filled and they don't screen properly. Okay, so that is why it's easier to remove the 4s electron of potassium compared to the 4s electron of iron. So that's like basically a factor of S block elements being more reactive and D block elements being moderately reactive. So these guys tend to lose the electron easily. They have really low ionization energies. D block they have slightly higher ionization energies. So that's like an effect that you will observe there. The second point we talked about is nuclear charge. So as the nuclear charge increases, what do you think will happen to the ionization enthalpy? Does it increase or decrease?
It would increase.
It would increase because if the nuclear charge is increasing, hold of the nucleus is increasing, matlab it's difficult to take that electron away. So your ionization enthalpy also increases. The third we are talking about is penetration effect. So penetration effect is similar to shielding effect, but it's a different case of the same thing. Like the logic, the concept behind it is the same, just that penetrating effect may the penetrating power of the different electrons of the same shell. So shielding effect, we're dealing with all of the inner electrons. Penetration effect, we're dealing with okay, agar nuclear pull hai for the third shell, then what is the effect of the nucleus on S shell versus P shell versus D shell versus F shell? That way. So the penetration power of S electron is maximum, followed by P, followed by D, followed by F. Okay. So if penetration power is more, so you can think of it as how well the nuclear pull is penetrating through the inner electrons and attracting the outermost electrons. So agar fourth shell ka hai, so if you compare 4s versus 4p versus 4d versus 4f, S electrons pe it's maximum, followed by P, followed by D, followed by F. Okay. Then comes electronic configuration. This is also pretty obvious. Half filled, fully filled configuration hai. So that means that stability is going to be like half filled and fully filled is more stable configuration. So which means that in configurations it is difficult to remove the outermost electron because it's already pretty stable. Atom doesn't want to give that away. So your ionization enthalpy is going to be slightly higher. So you can see that in the case of, if you compare nitrogen versus oxygen. So even though oxygen is a smaller atom compared to nitrogen, nitrogen ka ionization enthalpy will be more than oxygen because of the electronic configuration. In this case, it's half filled. In this case, it is not half filled. So it's going to have a more stable configuration that way. Okay. So you guys clear about these 4 points, how these factors affect ionization enthalpy?
Yes, ma'am.
Okay, awesome. So yeah, like based on this, you can, it's basically what I just said. So if you compare S and D metals, there's shielding effect coming into picture that's affecting the comparison of ionization enthalpy. Then if you go from top to bottom in a group, that's pretty straightforward. Size increases, it's easier to give away. So that's basically the nuclear charge coming into picture. Both of these actually. And if you compare elements in the same period, like left to right, then combination of nuclear charge. In very specific cases like nitrogen oxygen case, in the case of noble gases, then you will also consider electronic configuration as a reason. Okay, so that's about it for ionization enthalpy. It's already